Today's topic is an important extension on the language of graphical models, and it's intended to deal with the very large class of cases where what we'd like to do is not just write down a one-time graphical model for a particular application, but rather come up with something that is a general purpose representation that allows us to solve multiple problems using the same exact model. So to understand what that means in a somewhat more concrete setting, let's go back example of genetic inheritance that we've discussed previously. It's arguably the earliest example of Bayesian network reasoning, even before Bayesian networks were invented. And here we have as input a pedigree, which is a family tree, and we're interested in reasoning about a particular trait. And for each pedigree and each trait, we can construct a Bayesian network, and the Bayesian network might look like this. But clearly, if you had a somewhat different family tree, so suddenly you had another 3 cousins and a great-grandfather join the family tree, or if you had a different family altogether, you would still want to use the same sort of ideas, the same pieces of what we used in the first network to construct this other network, because there's clearly a lot of commonalities between them. So we have what you might call sharing between models. But in addition to that, you also have, in this example, as a fairly obvious sharing within the model. So for example, this CPD that tells us how Selma's genotype affects Selma's blood type presumably is the same process by which Marge's genotype affects Marge's blood type, and the same for Maggie and Lisa and Bart and Homer and everybody. So we have this tremendous amount of sharing of both dependency models and parameters. Similarly, you might looking at this, realize that the genetic inheritance model by which Bart's genotype is determined by the genotype of his 2 parents is the same inheritance model that applies to Lisa, to Maggie, to Marge, to Selma, and so on. So once again, we have a lot of parameters that are shared not just between, but also within the model. So we'd like to have some way of constructing models that have this large amounts of shared structure that allows us to both construct very large models from a sparse parameterization and also to construct entire families of models from a single concise representation. This is not the only such application. This is probably the most commonly used type of graphical models are those that have shared structure and shared parameters. So here is another example that we've seen previously. This is for natural language processing, a sequence model for, in this case, trying to identify named entity recognition. So a very common task for which graphical models have been used. And here also, we have a sequence model, and we have, again, shared pieces. For example, the parameters that relate the latent variable, in this case, what type of variable, what type of entity it is. Is it a person? Is it a location? And so on. There's a set of parameters here, and they're going to be independent of the place in the sequence in which we find the word, not because that's necessarily an exactly correct model. I mean, one could clearly imagine cases where the position in the sequence might make a difference, but because it's often a very useful simplifying assumption, specifically because it allows us to A, reuse parameters, and B, allow us to apply the same model to sequences of varying length without having to worry about what is my 15-word model versus what's my 8-word model. And so this is another case where you have a tremendous amount of reuse of parameters. We've already seen, similarly, the example of image segmentation. Clearly, we don't want to have a separate model for every superpixel within the image. There's hundreds of superpixels, so we have sharing across superpixels or pixels. So, for example, the model here that relates the class label of a superpixel to the image features of that superpixel is generally going to be shared. as are the parameters that involve adjacent superpixels. So these edge potentials are also going to be shared across, in this case, pairs of superpixels. These pairs of adjacent superpixels. And once again, we have sharing across models as well, because we are going to have one such model for image A, and obviously we don't want to construct a separate model for every image. So once again, we have sharing between and within a model. So let's look at one example a little bit more concretely, because it's an example that we're going to use in some of the later analysis. So now let's return to our university example, where we have a student who takes a class and gets a grade, and that grade depends on the student's difficulty, the difficulty of the course and on the intelligence of the student. Now, this is all fine if we're interested in reasoning just about an individual student, but now let's imagine that we want to think about an entire university. So now we have a difficulty variable. So these are all difficulty variables for different courses. In this case, C1 up to Cn are different courses that exist in our university. And conversely, on the other side, we have multiple students. And this is a set of intelligence variables that are indexed by different students. So we have the intelligence of student 1 up to the intelligence of student M. Now note that these are different random variables. They can and generally will take different values from each other, but they all share a probabilistic model, and that's sort of the kind of sharing that we have in mind. And what we see here is that the grade of a student within a course, which are these variables down here, depend on the difficulty of the relevant course and the intelligence of the relevant student. So for example, the grade of student 1 in course 1 depends on the difficulty of course 1 and on the intelligence of student 1. And once again, we have sharing of both the structure and the parameters across these different grade variables, so that they all have the same kind of dependency structure and the same CPD. Another example is that of robot localization, and this is another example of, in this case, a time series, where the robot moves through time from one position to the other, and although the position at time t is different, changes over time, we expect that the dynamics of the robot are fixed. And we'll talk more about that later. So that gives us a graphical model that, again, looks a little bit, this is one example of such a graphical model, where we see that the position, the robot pose over here, these x variables, depend on, for example, the previous pose and on whatever control action the robot took. And we're assuming that, once again, we have sharing of these parameters for each instantiation of this variable. So what that gives rise to is a class of models that are represented in terms of template variables, where a template variable is something that we end up replicating in many cases again and again within a single model as well as across models. And so the replication is indexed by the fact that the variable, you can think of it as a function that takes arguments. And the arguments, for example, might be time points, as in this example over here. So here we have a location variable that's indexed by a time point, or a sonar reading that's indexed by a time point. We have, in this case, a genotype variable and a phenotype variable that's indexed by a particular person, a label, a class label that's indexed by a pixel, and similarly the difficulty, the intelligence, and the grade that are indexed, in this case by different combinations of indices, course, student, or course-student pairs. And a template model is a language that tells us how template variables can be the dependency model for template variables and how concrete instantiations of variables, what are called ground variables, like the ones that are actually indexed by a particular time point or person, how they inherit the dependency model from.
Which of the following are advantage ของการใช้ template model capture event that occur in a time series CPD copy many times capture parameter sharing within a model capture distribution cannot be expressed in ordinary Bayesian network อันนี้น่าจะถูกตามอันนี้นะOkay,
and there is a whole range of such languages that have been developed in a special purpose way for different applications. So dynamic Bayesian networks are intended for dealing with temporal processes, for example, where we have replication over time. We have a whole range of languages for object relational models, both directed models and undirected models, where you have multiple objects such as people or students and courses or pixels. So people, courses, pixels, and lots of other things that can be related to each other in different ways. And how do you represent the dependency model over that ensemble in a coherent way? So there are many classes of models that allow us to represent in a single concise representation a template over rich models that incorporate multiple copies of the same variable and also allow us to represent multiple models within as a byproduct of a single representation. But one of the most commonly used among those is for reasoning about temporal models, where we have a system that evolves over time. So let's look at what we have. We represent a distribution over temporal trajectories. So the first thing we want to do when representing a distribution over continuous time is, in most cases, not always, is to try and forget that time is actually continuous, because continuous quantities are harder to deal with. So we're going to discretize time. And specifically, we're going to do that by picking a particular time granularity delta, which is the time granularity at which we're going to measure time. Now, in many cases, this is something that we already is given to us by the granularity of our sensor. So in many cases, for example, when we have a video or a robot, there is a certain time granularity at which we obtain measurements, and so that's usually the granularity that we'll pick. But in other cases, we might want to have a different granularity, so there is a choice here. So here's our time granularity, for example. And now we have a set of template random variables, x of t, and x of t denotes the value of a particular variable x being a template variable, x of t being a particular instantiation of that variable at time point t delta, so that we have multiple copies, one for each time point. Now, here is some notation that we're going to end up using later on, so to introduce it, where x of t denotes the variable x at time t, xt colon t prime denotes the set of variables between t and t prime. So a discrete in this case, because we've discretized time, so a finite set of random variables that spans these two time points inclusive. Now, our goal is that we would like to be able to have a concise representation that allows us to represent this probability distribution over the trajectory of the system of any duration. So we want to start at a particular time point. Usually this is going to be 0. And then what is the probability distribution over trajectories of arbitrary length? So how do we represent what is first of all, an infinite family of probability distributions, because you could look at trajectories of duration 2, 5, 10, a million, so that's an infinite family of distributions. And each of these is a distribution over an unbounded number of random variables, because if you have a distribution over a trajectory of length 1,000,000, you have to represent a 1,000,000-dimensional distribution. So how do we compactify that? How do we make that a much more concise representation? So there's different pieces to this. The first of those is what's typically called the Markov assumption. And the Markov assumption is effectively a type of conditional independence assumption. So it's the same building block that we use to compactify general purpose graphical models we're going to use here in the context of time course data. So here we're saying that the probability of the variable x, the set of variables x spanning the time from 0 all the way to capital T. So I haven't made any assumptions yet in this statement, so I'm just writing this down. I'm re-expressing it in terms of the chain rule for probabilities. There's no chain rule for Bayesian networks yet here. This is just the chain rule for probabilities. And the chain rule for probabilities in this context basically says that that probability is equal to the probability of x at time 0 times the probability of each consecutive time point, t plus 1, given, so this is the state at t plus 1, given the state at all previous time points, 0 up to t. So this is not in any way an assumption. This is just a way of re-expressing this probability distribution in the way that time flows forward. But it's not an assumption. You can represent any probability distribution over these random variables in this way. But now we're going to add this assumption. And this is an assumption. This is an independence assumption. And this independence assumption tells me that x of t plus 1, that is the state of time t plus 1, the next step, so this is the next step, is independent of the past given the present. So this is a forgetting assumption. Once you know the current state, you don't care anymore about your past. Okay? If you do that, we can now go back to this chain rule over here and simplify it. Because whereas before we conditioned on x up to 0, from time 0 to time t, now everything up to t minus 1 is conditionally independent, given. So all this is conditionally independent of t plus 1 given x of t, which means that I've allowed myself to move x of t here as the only thing that I'm conditioning on in order to determine the probability distribution of x t plus 1. So to what extent is this assumption warranted? So is this true? And let's take as an example, x equals the location or pose of a robot or an object that's moving. Is it the case that the location of the robot at t plus 1, so L of t plus 1, is independent of, say, L of t minus 1, just to simplify our lives, given L of t? Is this a reasonable assumption? Well, in most cases, probably not. And the reason is that it completely ignores the issue of velocity. Which direction are you moving and how fast? And so this is a classical example of where the Markov assumption for this particular model is probably too strong of an assumption. So what do we do to fix it? The one way to fix it is to enrich the state description so as to make the Markov assumption a better approximation. Just like any independence assumption, the Markov assumption is always going to be an approximation. But the question is how good of an approximation? And if we add, for example, v of t, which is the velocity at time t, and maybe the acceleration at time t, maybe the robot's intent, where its goal is, I mean, all sorts of additional stuff into the state, then at that point, the Markov assumption becomes much more warranted. Okay? And so that's one way of making the Markov assumption true. An alternative strategy, which we're not going to talk about right now, is to move away from the Markov assumption by adding dependencies that go further back in time. Back in time. And that's called a semi-Markov model. And we're not going to talk about that right now. The second big assumption that we are going to have to make in order to simplify the model is intended to deal with the question of, well, fine, so we've reduced the model to encoding a probability of x of t plus 1 given x of t, but it's still an unbounded number of conditional probabilities. Now, at least each of them is compact, but there's still a probabilistic model for every t. And this is where we're going to end up with a template-based model. We're going to stipulate that there is a probabilistic model p of x prime given x. X prime denotes the next time point, and x denotes the current time point. And we're going to assume that that model is replicated for every single time point. That is, when you're moving from time 0 to time 1, you use this model. When you're moving from time 1 to time 2, you also use this model. And that assumption, for obvious reasons, is called time invariance, because it assumes that the dynamics of the system, not the actual position of the robot, but rather the dynamics that move it from state to state, or the dynamics of the system, don't depend on the current time point t. And once again, this is an assumption, and it's an assumption that's warranted in certain cases and not in others. So let's imagine that this represents now the traffic on some road. Well, does the dynamics of that traffic depend on, say, the current time point of the system? On most roads, the answer is probably yes. It might depend on the time of day, on the day of the week, on whether there's a big football match, on all sorts of things that might affect the dynamics of traffic. The point being that just like in the previous example, we can correct inaccuracies in our assumption by enriching the model. So once again, we can enrich the model by including these variables in it. And once we have that, then again, the model becomes a much better reflection of reality. So now how do we represent this probabilistic model in the context of a graphical model like we had before? So let's now assume that our state description is composed of a set of random variables. So we have a little baby traffic system where we have the weather at the current time point, the location of, say, a vehicle, the velocity of the vehicle. We also have a sensor whose observation we get at each of those time points, and the sensor may or may not be failing at the current time point. And what we've done here is we've encoded the probabilistic model of this next state, so W prime, V prime, L prime, F prime, and O prime, given the previous state. So given W, V, L, and F. Why is O not here on the right-hand side? It's not here on the right-hand side because it doesn't affect any of the next state variables. So it would be kind of hanging down here if we included it. But since it doesn't affect anything, we don't choose to represent it. So this model represents a conditional distribution. Now we have a little network fragment. So this is a network fragment. And it doesn't represent a joint distribution. It represents a conditional distribution. The conditional distribution of the t plus 1 given t. But in order to represent that, we still use the same tools that we had in the context of graphical models. And so we can write that as the same kind of chain rule that we used before. So this would be the probability of W prime given W, based on this edge over here, times the probability of v prime, the velocity. So this says that the first one says that the weather at time t plus 1 depends on the weather at time t. The second one, that the velocity at time t plus 1 depends on the weather at time t and the velocity at time t, which indicates a certain persistence in the velocity, as well as the fact that, you know, if it's raining, you might slip sideways, so the velocity might change. Also, if you're careful, you might slow down if it's raining. And so again, there might be an effect of the weather on the velocity. The probability of the location at time t plus 1 given the location at time t and the velocity at time t. The probability of the sensor failure at time t plus 1 given the failure and at the previous time and the weather, which indicates that once the sensor is failed, it's probably more likely to stay failed, but maybe rain can make the sensor behave badly. And then finally, the probability of the observation at time t plus 1 given the location at time t plus 1 and the failure at time t plus 1. So there are several important things to note about this diagram that are worth highlighting. First of all, we have dependencies both within and across time. So here we have a dependency that goes from t to t plus 1. And here we have a dependency that is within t plus 1 alone. What induces us to make a modeling choice like this go one way versus the other? The assumption here is that this is a fairly rapid acting dependency. So that the observation is relatively instantaneous compared to our time granularity. And so we don't want that to go across time, but rather we want it to be within a time slice because it's a better reflection for which variable is it that actually influences the observation. Is it the current location or the previous location? So these kinds of edges, let's just give them names. These are called intra time slice edges, and these are called inter or between time slice. And a model can include a combination of both of these. Another kind of, a particular type of inter-time slice edge that's worth highlighting specifically are edges that go from a variable at one time point to the value of that variable at the next time point. These are often called persistence edges because they indicate the tendency of a variable to persist in state from one time point to another. Finally, let's just go back and look at the parameterization that we have in this model. So what CPDs did we actually need to include in this model? And we can see that we have CPDs for the variables on the right-hand side, the prime variables, but there's no CPDs for the variables that are unprimed, the variables on the left. And this is because the model doesn't actually try and represent the distribution over W, V, L, and F. It doesn't try and do that. It tries to represent the probability of the next time slice given the previous one. So as we can see, this graphical model only has CPDs for a subset of the variables in it, the ones that represent the next time point. So that represents the transition dynamics. If we want to represent the probability distribution over an entire system, we also need to provide a distribution over the initial state. And this is just a standard generic Bayesian network, which represents the probability over the state at time 0 using some appropriate chain rule. So nothing very fancy here. With those two pieces, we can now represent probability distributions over arbitrarily long trajectories. So we represent this by taking for time slice 0 and copying the time 0 Bayesian network, which represents the probability distribution over the time 0 variables. And now we have a bunch of copies that represent the probability distribution at time 1 given time 0. And here we have another copy of exactly the same set of parameters that represents time 2 given time 1. And we can continue copying copying this indefinitely, and each copy gives us the probability distribution of the next time slice given the one that we just had, and so we can construct arbitrarily long Bayesian networks. So to make this definition slightly more formal, we define the notion of a 2-time slice Bayesian network, also known as a 2TBN. And a 2TBN over a set of template variables x1 up to xn is specified as a Bayesian network fragment along exactly the same lines that we used in the example. The nodes have 2 copies. The next time state variables x1 prime up to xn prime, and some subset of x1 up to xn, which are the variables, the time t variables that affect directly the state at t+1. Okay? And because we want this to represent a conditional probability distribution, only the time t+1 nodes have parents and a CPD, because we don't really want to model the distribution over the variables of time t. And the TTBN defines a conditional distribution using the chain rule, using something that looks exactly like the chain rule. So the probability of x prime given x is the product of each variable in time t+1, so only the prime variables given its parents, which may be in time t+1, time t, or a combination of both. A dynamic Bayesian network is now basically defined by a 2TBN, which we just defined, and a Bayesian network over time 0. So this is the dynamics, and this is the initial state. And we can use that to define arbitrary probability distributions for, probability distributions over arbitrarily long trajectories using what's called the unrolled network, or also called the ground network. And this is exactly as in the example that I showed. The dependency model for time 0 is copied from the BayesNet for time 0, and this is the transition is copied from the BayesNet that denotes the conditional probability for transitions.
So before we conclude this lecture, let's look at an example of a dynamic Bayesian network that is a more realistic one than the simple examples that we've shown before. This is a network that was actually designed for tracking vehicles in a traffic situation. And so we can see that there are multiple variables here that represent both the position and velocity of the vehicle. Both in an absolute sense. For example, this is x dot and y dot are the velocities, as well as various more semantic notions of location, like whether you're in the lane. There are contextual variables, such as left clear and right clear. The engine status, for example, as well as what the driver is currently doing. For example, the forward action and the lateral action. We can see that there are persistence edges that denote the persistence of various forms of the state from time t to time t+1, as well as a variety of these intermediate variables over here that allow us to represent the probability distribution in a more compact way by incorporating variables that do not persist, or at least in the simplified model do not persist. And finally, we see that there are a large number of sensor observations, such as turn signal, whether the car is clear on the right and on the left, or appears to be clear on the right and the left, and so on. So this is a much more realistic model of how traffic evolves than the simplified one that we saw before. To summarize, dynamic Bayesian networks provide us with a language for encoding structured distributions over time. And by making the assumptions of a Markovian evolution as well as time invariance, we can use a single compact network to allow us to encode arbitrarily long transitions over arbitrarily long time sequences. But these assumptions that we made, the Markovian assumption and the time invariance assumption, are not immediately correct and might require that we redesign the model so as to so as to make these assumptions a better approximation to the true underlying distribution by, for example, adding variables, as we showed.
Be failing at the fact that, if it's raining, give them the notion of a 2-time slice. And the TT, what's called the unrolled